Okay, so I want to talk about a pretty important principle, and that is the principle of duality. And what it tells us is that if you have any kind of a propositional statement, there's actually a dual statement that is going to have the same truth value. So if our original statement is true, the dual statement is also true. So here's how we do it. Let's take any kind of a statement, like for example, x and false, or true. Okay, that should be equal to true. Okay, this is in fact a true statement in propositional logic. But now let's define the dual statement, and the dual statement looks like this. So the dual statement, we're simply going to copy all the symbols over. So start with x, but ands are going to become ors. So we have x or, and false will become true. Likewise, ors become and true becomes false. And that should be equal to true, which becomes false. Okay, so that's the way that we do dual statements. When we have an or, we convert that to an and. When we have an and, we convert that to an or. True, we convert into false. And false, we convert into true. Okay, so this is our original statement, and this is the dual statement. Okay. Now, we're going to be able to prove all these dual statements kind of with a very simple proof strategy. Okay, so our proof strategy will be number one. We're going to start with the dual statement. Okay, because that's what we're trying to prove. Okay. And then we're going to use double negation. And what we're doing with double negation is basically this will convert x into not x everywhere, right? Y's into not y's, and so on. That's what we're going to use double negation for. Now our third step will be to use De Morgan's law. And what that will do is it will move the not will move to the front. And then we'll use the original theorem. So here's the idea. We'll have something like this, and then we'll use the original theorem there to convert it into whatever the right-hand side is supposed to be. And then when we're done with that, we have a negation on that, so we'll use De Morgan's law again. And then finally double negation to get everything back. So this general strategy is actually going to work pretty well for most of these dual theorems. So let's give that a shot. Okay, so let's try to make that concrete. So let's look at a specific theorem. So we have the original theorem, and the original theorem that I'm going to use is or null, which is one of our axioms about or, and it looks like x or true is equal to true. Okay, and so the dual statement that we're going to prove is x and false, right? See how I'm turning ors into ands, true into false? That should be equal to false. Okay, so let's go ahead and prove it. So we start with the left-hand side, x and false, and we'll say that that is equal to, well, that we'll use double negation. So this is equal to not x and false, and that's because of double negation. Okay, I'd like to now use De Morgan's law, right? But before I can actually do that, I need to have nots here. Okay, and I have one, but I don't have a not there. But I can prepare myself for that by turning false into not true. Okay, now why can I do that? Well, I can do that because of the truth table. Okay, so then now what? Okay, so now I do have two nots, so I can in fact invoke De Morgan's. This will be equal to not of not x or true. And now I will use the original theorem, but on that section here. You see the original theorem is x or true is equal to true. I have here something not x or true, so I can in fact do that. This is just simply true, okay, by the original theorem, which was or null. Okay, and in this case, I don't even need to go through, I don't need to push the not inside or any of that work, because this side is so simple. This is just simply equal to false, and that is again because of the not truth table. Okay. So that's how we prove these. Okay. So remember the strategy, because you'll see it over and over again. What we'll do is we'll use double negation to change all of our variables. We're actually preparing to be able to use De Morgan. Then we'll use De Morgan. We have not one big expression. We use the original theorem on that big expression, and then we have to push the not back in, usually using De Morgan's and double negations. In this case, we didn't have to, because it was so, well, we were done. And that's the end of the proof.